Hello students, I hope you all are doing good. Today we are going to discuss NCERT section 9.7 and 9.7.1 of chapter Ray Optics and Optical Instruments. This is the disclaimer. So the first learning objective is to understand the principles and construction of basic optical instruments such as simple and compound microscopes. These instruments are crucial in magnifying objects, allowing us to explore the microscopic world. As we discuss this, pay attention to how each component contributes to the overall function of the microscope. Moving on to our second objective, we will apply mathematical analysis to calculate magnification. This involves understanding how lenses work together to enlarge images. We will also explore the evolution of microscope features and modern developments, highlighting how advancements have improved our ability to observe minute details. Remember, magnification is key to enhancing our observational capabilities. In this lecture, we are going to cover NCERT section 9.7 optical instruments and section 9.7.1 the microscope. Here we have an image showcasing various optical instruments. Notice how these devices are designed to assist in viewing objects that are either too small or too distant for the naked eye. This visual sets the stage for our deeper dive into their functionalities. Optical instruments are crucial because they extend our natural vision capabilities. They allow us to see things that are otherwise invisible or unclear. This is achieved through the manipulation of light, which we will explore further. The core of optical instruments lies in their use of mirrors, lenses, and prisms. These components work together to bend and focus light, enabling us to see objects more clearly. Understanding how these elements interact is key to grasping the operation of these devices. Now, the design of optical instruments is grounded in the laws of reflection and refraction. Those fundamental principles dictate how light behaves when it encounters different surfaces, which is essential for the effective functioning of these instruments. Modern optical instruments benefit from advanced materials and precision manufacturing. This means they are more efficient and accurate than ever before, allowing us for a wide range of applications in science, medicine, and everyday life. So let's begin with the classification of optical instruments. Okay, so the first classification by function. Optical instruments can be categorized based on what they do. Okay, this helps us appreciate the variety of tools available for different optical tasks. The first category under function is magnifying instruments. These include microscopes and magnifying glass, which are designed to enlarge the appearance of objects. Think how a magnifying glass helps us to see small details more clearly. Next, we have distance instruments like telescopes and binoculars. These are used to view distant objects, bringing them closer to our eyes. Imagine using a telescope to observe stars and planets far away in the night sky. The final function-based category is imaging instruments, such as cameras and projectors. These devices capture or display images, playing a crucial role in photography and presentations. Consider how a camera captures moments in time. Now let's shift to the second classification by construction. This focuses on the materials and methods used to build the instruments. Understanding this helps us why certain instruments are better suited for specific tasks. So refracting type instruments are the first type under construction. They primarily use lenses to bend light. A common example is a simple magnifying glass which uses a lens to focus light and enlarge the images. Reflecting instruments, on the other hand, use mirrors to direct or deflect light. Telescopes often use mirrors to gather and focus light from distant stars. This method allows for larger and more powerful instruments. So we will study now the design considerations for optical instrument. The first consideration is magnification. This refers to how much larger an image appears compared to the actual object. It's crucial for applications like microscopes and telescopes, where seeing details is important. Think of it as zooming in on a picture to see more detail. Next, we have resolution. This is the ability of an optical instrument to distinguish fine details. High resolution means you can see two close objects as separate entities. Okay, if two objects are placed very, very close to each other, that you cannot see them as a separate object. You cannot distinguish them. Okay, so this is the design consideration for optical instrument, that they have the ability, they have high resolution, so that we can see the object as separate entities that are placed by some distance, which is very, very small. So our naked eye cannot resolve them, but the optical instrument can resolve them, and we can see the object as separate entities. It's like adjusting the focus on a camera to get a clear, sharp image. Now let's talk about field of view. This is the angular extent of observable area visible through the lens or mirror. So the area of a view, okay, or up to what extent we can see, up to what extent the landscape we see through the optical instrument. Okay, like side mirrors are used in vehicles. Side mirror consists of convex mirror. So field view of convex mirror is more. It can capture more area than concave mirror. So that's why it is used in side mirrors, so that we can see the area behind us or vehicles coming behind us. Okay, so wider area, wider field of view allows us to see more of the scene at once. Similar to how a wide angle lens on a camera captures more of the landscape. Another important factor is light gathering power. This is the instrument's ability to collect light, which is essential for producing bright images, especially in low light conditions. Okay, imagine trying to see in the dark. The more light you can gather, the better you can see. Okay, also night vision cameras. Okay, they gather more light. The light gathering power for these lenses used in these cameras are more. Okay, so they gather light more in low light conditions, and the image formed is bright. Finally, we have aberration correction. This involves minimizing optical distortions or defects in images that can blur or distort the image. It's like using corrective lenses in glasses to ensure you see clearly without any distortion. Humana is the most important optical device which helps us to see the beautiful world around us. Here we have an image of a microscope and a telescope. These are two of the most important optical instruments used in science. Notice their structure and design, which are optimized for their specific functions. The microscope allows us to see tiny details, while the telescope helps us observe distant objects. Keep their images in mind as we discuss their principles. Okay, so what microscope do? Their principle is to show us the magnified image. But what microscope do? It magnifies the very, very small objects. What telescope do? It shows the magnified image. It bring the object closer to our eyes. Okay, object is already highly magnified. Planets, moon, okay, stars, they are highly magnified, but they are at a very high distance from us. So telescope brings that distant objects closer to our eye. Okay. Now let's delve into the principles and working of these instruments. The microscope and telescope operate on similar optical principles, but they are designed for different purposes. Understanding these principles will help us how they magnify objects and why they are crucial in scientific exploration. We will break down their components and how they work together to achieve magnification. So now we will discuss about the microscope in this lecture. We will discuss about two type of microscopes, simple and compound. Here we have an image of a simple microscope. Notice its compact design, which is essentially a single converging lens. Okay, single convex lens. This image helps us visualize the basic structure of a simple microscope, which is crucial for understanding its function. Let's delve into the details of simple microscope. It's essentially a magnifying glass which uses a single lens to enlarge the objects. This simplicity make it an accessible tool for magnification, perfect for everyday use. A key feature of simple microscope is its single converging lens with a short focal length. This design allows it to magnify objects effectively. Okay, remember, the shorter the focal length, the greater the magnification. Okay, if a convex lens has shorter converging lens, or convex lens has shorter focal length, it means it will produce greater magnification. So when using a simple microscope, the object is placed within the focal length of the lens. This positioning creates a virtual erect and magnified image, allowing us to view the object comfortably at a distance of 25 centimeter or more. This is crucial for reducing eye strain during prolonged observation. Okay, so we have to produce the magnified image and erect image and virtual image. So object is placed within the focal length of the converging lens that is used in simple microscope. Okay, so then image is formed at a distance of 25 centimeter, that is called near point or least distance of distinct vision, or more than this distance. Okay, so we have to reduce the eye strain during prolonged observation. The principle behind the simple microscope is fascinating. When an object is placed between the focal length and the optical center of the lens, the light rays diverge. This divergence makes the object appear larger and closer, enhancing our abilities to observe fine details. Here we have two images illustrating the setup of simple microscope. On the left, the magnifying lens is positioned so that image is at near point, okay, D, which is closest point at which eye can focus comfortably. On the right, the object is near the focal point of lens and the image appears far off but closer than infinity. These images help us visualize how the lens manipulates light to magnify the objects. Okay, so you can see in the first diagram, figure 2.9.23, A part. Okay, object is placed within the focal length and image is formed at D, least distance of distinct vision, that is 25 centimeter. Okay, now object is placed on the focus of convex lens. So image is formed at infinity. Okay, so first case is strained eye. Okay, object image formed at near point, and second case is image formed at infinity, or we can say relaxed eye condition. Now let's consider what happens when object is placed at a distance equal to the focal length of the lens. In this scenario, the image is formed at infinity. This means the light rays are parallel after passing through the lens, making the image appear very far away. This setup is useful for reducing eye strain when viewing objects for extended periods. However, if we move the object slightly closer to the lens, just less than the focal length, the image becomes virtual and appears closer than infinity. This adjustment allows us for a more comfortable viewing experience as the image is easier to focus on. This principle is crucial for understanding how microscopes can be adjusted for optimal viewing. Now let's talk about viewing comfort. Although the closest comfortable distance for viewing an image is at near point, which is 25 centimeter. This can strain the eye. This is an important consideration when using microscopes, as long time use can lead to eye fatigue. Okay, so eye can be strained. So to reduce the eye strain, forming the image at infinity is often preferred. This allows eyes to remain relaxed, making it easier to view the image for extended periods. This is a key point for anyone using microscopes regularly, as it enhances comfort and usability. Okay, when we look at very close object for a long time, when we study, when we look at the book for a long time, our eyes get strained and start paining. Okay, then it is recommended that look at distant objects so that I feel relaxed. Okay, so that is the concept here. Finally, we see both scenarios depicted in figure 9.23. The first scenario shows the object at near point, while the second shows the image at infinity. Understand these two cases help us appreciate the flexibility and adaptability of microscopes in different viewing conditions. Let's start by looking at the magnification analysis of a simple microscope. Here we have two images illustrating the setup in figure 9.23 part A, showing the magnifying lens positioned so that the image is at the near point, which is crucial for maximum clarity. Part B demonstrates how the angle subtended by the object remains consistent with that at the near point. Notice how these images help visualize the concept of magnification. Okay, in the A diagram, it is again the same diagram in which image is formed at near point and object is placed within the focal length. And B diagram, so angle made by or angle subtended by object on the eye, at the eye, when it is placed at near point. Okay, object is within the focal length, but eye can see the object comfortably at 25 centimeter near point. So we will take the object at least at near point, and the angle subtended by the object placed at near point or taken to be at near point at the eye is called the visual angle for object. Now we will discuss the first case when the image is at near point, which is typically 25 centimeters from the eye. This is a standard reference point in optics known as the least distance of distinct vision. Understanding this helps us calculate the magnification more accurately, as it provides a baseline for comparison. The linear magnification M. In this point, we introduce the formula for linear magnification, denoted as M. This formula is essential for determining how much larger the image appears compared to the actual object, where V is the image distance and U is the object distance. The formula also incorporates the focal length f of the lens, which is a key factor in the magnification process. Finally, look at the mathematical expression for magnification. The equation M equals to V by U equals to V multiplied by 1 by V minus 1 by F shows how magnification is calculated using the lens formula. Okay. This relationship is fundamental in optics as it connects the image and object distances with the focal length. Understanding this equation allows us to predict how changes in these variables affect the magnification. Now let's look at the formula for magnification M equals to 1 minus 1 by F, V by F. In this equation, M represents magnification, V is the image distance, and F is the focal length of the lens. The formula helps us calculate how much larger the image appears compared to the actual object. In this point, we consider a specific case where the image is virtual, meaning it appears on the same side of the object. Here v is equal to minus d, where d is the least distance of distinct vision, or we can say near point. This concept is important because it affects how we perceive the magnified image. Finally, we adjust our magnification formula to account for the virtual image m equals to 1 plus d by f. This is equation 9.39. It shows how the magnification changes when image is virtual, emphasizing the role of the focal length and the least distance of distinct vision in determining the final magnification. Here we have an image of simple microscope labeled as figure 9.23. Notice the key components and how they are arranged. The setup is essential for understanding how light is manipulated to magnify objects. Pay attention to the path of light through the lenses, as this is fundamental to the microscope's function. So this diagram is for image formed at infinity. Okay, so object is placed at focal length, focus, at a distance of equal to focal length. Okay, so eye is relaxed here. So image is formed at infinity. So angle subtended by the image at the eye is equal to theta I here. Okay, but angle subtended by object at the eye is not theta I. Even in the diagram it is visible that it is theta I, but it is not actually theta I. Why it is not theta I? Because object should be placed at near point at least. Here object is not at near point. So angle subtended by object to the eye will be taken when object is to be taken at near point. Okay, so case 2, image at infinity, or we can say relaxed eye. So let's consider the case where the image is at infinity, which is when the eye is relaxed. This is an important scenario because it allows for comfortable viewing without eye strain. In this setup, the microscope is adjusted so that the final image appears to be at infinity, making it easier for the observer to see details clearly. Now let's talk about magnification. The formula m equals to h dash by h tells us magnification is the ratio of the image size to the object size. Here h is the size of the object and h dash is the size of the image. This relationship is key to understanding how microscopes enlarge the view of small objects. Finally, this magnification can also be described as the ratio of the angle subtended by the image to the angle subtended by the object when placed at a distance d for comfortable viewing. This concept helps us understand how the microscope enhances our ability to see fine details by increasing the apparent size of the object. Now let's talk about magnification when image is at infinity. This is a specific condition where image formed by the microscope appears to be at infinite distance. This setup is often used to reduce eye strain during prolonged observation. We will explore how this affects the magnification process. In this scenario, we need to calculate the angular magnification. Angular magnification is a key concept in optics as it describes how much larger the image appears compared to the object itself. This is particularly important when the image is at infinity, as it helps to quantify the effectiveness of the microscope. Angular magnification is defined as the ratio of angle subtended by the image to the angle subtended by the object at eye, with both at the near point, typically 25 centimeters. This definition helps us understand how microscopes enhances our ability to see details by increasing the apparent size of the image. Now consider the object we were observing. If the object has a height h, the maximum angle it can subtend without a lens is when it's at near point, a distance d from the eye. This is crucial because it sets the baseline for understanding how magnification works. The angle subtended by the object at this near point is what we focus on next. This angle is a key factor in determining how much the object is magnified when viewed through the microscope. So here we have mathematical expression for the angle subtended by the object. So angle subtended by the object is not theta I, but theta naught. Why? Because we are taking object to be at near point. Then angle subtended by the object to be taken as theta naught. Okay, when object is placed at near point, that is equal to 25 centimeter. This formula shows the relationship between the object's height, the distance to the near point, and the angle subtended. Understanding this relationship help us quantify the magnification achieved by the microscope. When the object is placed at focal point of the lens, the image is formed at infinity. This is an important concept because it allows the eye to view the image without strain. As the eye is relaxed when looking at the object at infinity, the principle is key to how microscopes enhance our ability to see the small details. Next, we calculate the angle subtended at the eye by the image when the object is at focal point. This angle is crucial for determining the magnification power of the microscope. Understanding this angle helps us quantify how much larger the image appears compared to the actual object. The formula for the angle theta I equals to h upon f is derived from the geometry of setup shown in the figure 9.23c. Here h represents the height of the object and f is the focal length of the lens. This equation is fundamental in calculating the magnification provided by the microscope. Now, angle subtended by the image is formed at infinity. Okay, so now angle subtended by the image is theta I. So it is theta I is equal to, in the C part of figure 9.23, theta I is equal to h upon f. Okay. Now let's discuss angular magnification. This is crucial concept because it helps us understand how much larger an object appears when viewed through a microscope compared to the naked eye. Angular magnification is the ratio of the angle subtended by the image to the angle subtended by the object. Here we have the formula for angular magnification. M equals to theta I upon theta naught equals to d upon f. In this equation, theta I is the angle subtended by the image, theta naught is the angle subtended by the object, d is the least distance of distinct vision, and f is the focal length of the lens. This formula shows how the focal length and the distance of distinct vision affect the magnification. Finally, let's compare this magnification to when the image is at near point. Although the magnification is slightly less, viewing is more comfortable, which is often preferred in practical application. The difference in magnification is usually minimal, making this method advantageous for long time observation. Okay, so this magnification is 1 less. The magnification in the case of near point is 1 plus d upon f. So this magnification in the case of image formed at infinity is d upon f, which is 1 less than the magnification produced in that case where image is formed at near point. Okay, but this method is preferred. Why? Because in this case eye is relaxed, so strain on the eye is minimized. Okay, although its magnification is slightly less, but it does not affect much the magnification. Okay, magnification is slightly less, but viewing is more comfortable. So here we have the image illustrating the ray diagram for a compound microscope. This diagram is crucial as it shows how light travels through the lenses to form an image. Pay attention to the path of the rays and how they converge to form a magnified image. Okay, now in this diagram you can see object is placed in front of the objective lens. Okay, image is formed and A dash B dash. Now this image will act as a object for the second lens, and second lens will form the final image. Okay, let's discuss the limitation of simple microscope. It typically offers a maximum magnification of 9x, means 9 times, maximum 9 times the object, due to realistic focal length. This limitation is important to understand why more complex microscopes are necessary for higher magnification. To achieve much larger magnifications, we use a compound microscope which employs two lenses. This setup allows one lens to enhance the effect of the other, significantly increasing magnification. This principle is key to understanding how compound microscopes work. Finally, the schematic diagram we have seen earlier is a representation of compound microscope. This diagram helps us visualize the arrangement and function of the lenses within the microscope, reinforcing our understanding of its operation. The compound microscope uses two lens system, the objective and the eyepiece. This dual lens setup is key to achieving high magnification, allowing us to see details that are invisible to the naked eye. Emphasize the importance of each lens in the magnification process. Let's focus on the objective lens. It's a convex lens with a small focal length and aperture. This lens creates a real inverted and magnified image of the object. The small focal length is crucial for achieving high magnification, which is why the objective lens is so important. Now the eyepiece, which is also a convex lens but with a larger focal length, it acts as a simple microscope, allowing us to view the image formed by the objective lens. Okay, so firstly image is formed by the objective lens. Then this image will be acting as object for the eyepiece. And this image is formed within the focal length of eyepiece. So eyepiece will act as a simple microscope. It will form a magnified virtual image of this image formed by objective. It will form final virtual erect image. Okay. Erect image with respect to the intermediate image, but it is inverted with respect to the object. Okay, so it acts as a simple microscope, allowing us to view the image formed by the objective lens. This combination of lenses is what makes the compound microscope so powerful. Now let's talk about magnifying power, also known as angular magnification. This is a key concept in understanding how microscopes enhance our vision. The magnifying power is the product of the magnification by the objective lens and the eyepiece. This means that both lenses work together to enlarge the image, and we will explore how each contributes to that overall magnification. Here is the formula for magnifying power. M equals to M naught multiply ME. In this equation, M naught represents the magnification by the objective lens and ME is the magnification by the eyepiece. Understanding this formula is essential for calculating the total magnification of a microscope. We will discuss how changing each component affects the final image size. The first key point is that the initial image formed by the objective lens is inverted and located near the focal plane of the eyepiece. This positioning is essential for the eyepiece to further magnify the image. Remember, the focal plane is where light rays converge to form a clear image. When the first inverted image is precisely at the focus of eyepiece, the final image is projected at infinity. This means the viewer can see the image without straining their eyes, as the light rays are parallel. This setup is ideal for comfortable viewing over extended periods. Finally, it's important to note that the final image is inverted compared to the original object. This inversion is a characteristic of a compound microscope optical system. Understanding this helps us appreciate how the microscope alters our perception of the microscopic world. Now let's talk about objective magnification. This is a key concept in understanding how microscopes work. The objective lens is responsible for their initial magnification of the specimen. It's important to grasp how the magnification is calculated as it affects the overall magnification of the microscope. Here's the formula for objective magnification. M naught equals to H dash upon H equals to V naught upon U naught. In this equation, H dash is the height of the image, H is the height of the object, V naught is the image distance, and U naught is the object distance for objective lens. Each of these variables plays a crucial role in determining how much object is magnified. When the object is placed close to the focal point of the objective lens, we can make some approximations. Specifically, U naught approximately equal to minus F naught and V naught approximately equal to L, where L is the tube length of the microscope. These approximations simplify our calculation and help us understand the relationship between the object and the image distances. Okay, so when we consider the object distance to be at focus of objective, nearly equal to focus of objective lens, then image is formed at near the eyepiece. Okay, or we can say the distance of image distance in this case will be equal to tube length. Tube length is the distance between objective and eyepiece. Okay, so if the object is placed near the focus of the objective lens, then image will be formed near the eyepiece. That means image distance will be nearly equal to tube length. Okay, so using these approximations, we derive the formula M naught equals to L upon F naught. This equation shows the magnification is directly proportional to the tube length and inversely proportional to the focal length of the objective lens. This relationship is crucial for designing microscopes with the desired magnification capabilities. Next, let's discuss the eyepiece magnification. The eyepiece is the lens you look through, and it plays a significant role in magnifying the image further. Understanding how the eyepiece contributes to the overall magnification is key to grasping the microscope's function. The angular magnification of the eyepiece, denoted as ME, is calculated using the formula similar to that of the simple microscope. This formula helps us determine how much larger the image appears compared to the actual object. It's important to note that the final image forms the image at near point, okay, which is crucial for clear vision. Here's the formula for eyepiece magnification. ME equals to 1 plus D upon FE. Okay, so eyepiece here is acting as simple microscope, and for simple microscope, the formula for magnification when image is formed at near point was M equal to 1 plus D upon F. Okay, so for eyepiece it is ME equal to 1 upon D upon 1 plus D upon FE. Okay, so in this equation, D represents the near point distance, typically 25 centimeter, and FE is the focal length of the eyepiece. Understanding this formula allowing us to calculate how much the eyepiece magnifies the image. Remember, the larger the ME, the more magnified the image. So here's the formula for the angular magnification due to the eyepiece. ME equals to D upon FE. In this equation, D represents the least distance of distinct vision, typically around 25 centimeter, and FE is the focal length of the eyepiece. This formula helps us calculate how much the eyepiece magnifies the image when image is formed at infinity. So mark it as 9.44 B equation. Okay, so when image is formed at infinity, what is the magnification formula for simple microscope? That is M equal to D upon F. So when image is formed at infinity, so for eyepiece, magnification of eyepiece will be equal to D upon FE. Okay. Now let's talk about the total magnifying power of the microscope. This is the combination of magnification provided by both objective lens and the eyepiece. Understanding this will help us appreciate how microscopes can magnify object to such great extent. For image at near point, the formula for total magnifying power when the image is at near point is m equals to m naught multiplied me equals to L upon f naught multiplied by 1 plus d upon fe. Here L is the tube length, f naught is the focal length of the objective lens, and m naught is the magnification of objective. This formula shows how both lenses contribute to the overall magnification. Alternatively, when the image is formed at infinity, the formula for magnifying power changes slightly. This is another common setting for microscopes, especially when the user wants to reduce eye strain during the prolonged observation. So for an image at infinity, the magnifying power is given by m equals to L upon f naught multiply d upon fe. This formula highlights the relationship between the tube length, focal length, and the least distance of distinct vision in determining the magnification. So let's start by looking at the design example of a compound microscope. This will help us understand the practical application of the concept we are discussing. So in this example, we have microscope with the specific focal lengths. These are crucial for determining how the microscope magnifies object. Let's delve into the details. So here we have focal length of objective and eyepiece lenses. F naught equals to 1 centimeter and Fe equals to 2 centimeter. These values are essential for calculating the magnification. Additionally, tube length equals to 20 centimeter and least distance of distinct vision D equals to 25 centimeter are given. These parameters will help us compute the total magnification. Now let's calculate the total angular magnification of the process of the microscope. This is a key concept as it tells us how much larger the microscope makes the object appear. Using the formula m equals to L upon f naught multiplied by d upon fe, we substitute the values to find the magnification. This step-by-step calculation is crucial for understanding the process. The result of calculation m equals to 250. This means microscope magnifies the object 250 times its actual size. This is a significant magnification, allowing us to see fine details. So we are given a compound microscope with a total magnifying power of 30 and an eyepiece of focal length 5 centimeter. The final image is formed at least distance of distinct vision, which is 25 centimeter. We need to calculate the magnification produced by the objective lens. Okay, magnifying power m, this is the total magnification provided by the microscope given as 30. Focal length of eyepiece Fe is given. The distance at which the eyepiece lens focus light given as 5 centimeter. And least distance of distinct vision D, the closest distance at which the eye can see an object clearly, typically 25 centimeter. So let's begin by understanding the formula for the magnifying power of a compound microscope. It's important to note that the total magnifying power is the product of the magnification produced by the objective lens and the eyepiece. This relationship is crucial for solving our problem. So here is the formula m equals to m naught multiplied by me. This equation tells us that the overall magnification is a result of both objective and the eyepiece working together. Each component plays a vital role in enhancing the image. Now let's identify the values given in the problem. We know that total magnifying power is 30. This is the combined effect of both lenses, and we will use the information to find the magnification of the objective lens. The magnifying power denoted as m is given as 30. This is a key piece of information that we will use to calculate the unknown magnification of the objective lens. The focal length of eyepiece is 5 centimeter. This parameter is essential because it influences the magnification produced by the eyepiece, which we will need to consider in our calculation. The least distance of distinct vision is 25 centimeter. This is the distance at which the final image is formed, and it's a standard value used in optical calculations. It helps us determine the magnification produced by the eyepiece. To solve this, we first need to determine the magnification produced by the eyepiece. This is a crucial step because the total magnification of the compound microscope is the product of the magnification of eyepiece and the objective. Let's introduce the formula for the eyepiece magnification. So here is the formula for the magnification produced by the eyepiece, denoted as ME, equals to 1 plus D upon FE. In this formula, D is the least distance of distinct vision, which is 25 centimeter, and FE is the focal length of the eyepiece, given as 5 centimeter. This formula helps us understand how the eyepiece contributes to the overall magnification. So substituting the values, after substituting the values, we find that ME equals to 1 plus 25 centimeter upon 5 centimeter, which simplifies to ME equals to 1 plus 5 equals to 6. This means the eyepiece alone magnifies the image 6 times. This calculation is a key part of understanding the microscope's overall magnifying power. Now let's substitute the magnification of the eyepiece back into the magnifying power formula. This step is crucial because it allows us to connect the known values with unknown magnification of objective lens. Pay attention to how we set up the equation, as this will guide us to the solution. Here we have the equation M equals to M naught multiplied ME, where M is the total magnifying power, M naught is the magnification of the object, and ME is the magnification of the eyepiece. We have substituted the known values 34M and M naught, 34M and 6 for ME. This equation is the key to finding the magnification of the objective lens. Next, we solve for the magnification produced by the objective lens, denoted as M naught. This step involves simple algebraic manipulations, but it's important to understand how each variable contributes to the overall magnification of the microscope. So by dividing 30 by 6, we find that the magnification produced by the objective lens is 5. The result shows that objective lens contributes significantly to the overall magnifying power of the microscope. Finally, we conclude the magnification produced by the objective lens is 5. This is a critical piece of information because it tells us how much the objective lens enlarges the image before it reaches the eyepiece. Let's look at how optical instruments are classified. They can be grouped by their functions such as magnifying, distance measuring, imaging, and analysis. Additionally, they are categorized by their construction, including refracting, reflecting, and catadioptric designs. Understanding these classifications help us appreciate the diversity and specialization of optical instruments. Now let's discuss the key design factors of optical instrument. These include magnification, which determines how much larger an object appears; resolution, which affects the clarity of the image; field of view, which is extent of the observable area; and light gathering power, which influences brightness; and aberration correction, which ensures image accuracy. Each of these factors play a crucial role in the effectiveness of an optical instrument. Finally, let's consider a simple microscope, commonly known as a magnifying glass. It uses a single converging lens to produce virtual, erect, and magnified images. This basic yet powerful tool exemplifies how optical principles can be applied to enhance our ability to see fine details. Let's start by discussing the magnification of simple microscope. The magnification depends on where the image forms. If the image forms at a near point, the magnification is given by the formula M equals to 1 plus D upon F. If it forms at infinity, the magnification is equal to M equal to D upon F. Here D is the least distance of distinct vision, or we can say near point, typically 25 centimeter, and F is the focal length of the lens. Now let's move on to the compound microscope. It uses two lens system, the objective lens and the eyepiece. This setup allows us much higher magnification than a simple microscope. The objective lens creates an enlarged image which is further magnified by the eyepiece. This dual lens system is crucial for observing very small details. Finally, let's look on the formula for the total magnification of a compound microscope. It's given by L upon F naught multiplied by D upon Fe, where L is the tube length, F naught is the focal length of the objective lens, and Fe is the focal length of the eyepiece. This formula shows how the focal length changes and tube length contributes to the overall magnification. Remember, adjusting these variables can significantly change the magnification. So let's see the practice questions. In first question, you have to write the formula for a total magnification of a compound microscope in terms of tube distance, objective focal length, eyepiece focal length, and near point distance. Let's reveal the next question. In a simple microscope, also known as a magnifying glass, the object must be placed within the focal length to produce a virtual image. This is crucial because it allows the lens to bend light rays in such a way that they appear to diverge from a larger image. Now consider a microscope, simple microscope with a focal length of 5 cm. We want to calculate its magnification when the image is formed at near point, which is typically 25 cm. Remember, magnification is the ratio of image distance to the object distance. And in this case, it's simplified by the near point distance. Moving on to the next question, let's identify the two main lens system in the compound microscope, the objective lens and the eyepiece. The objective lens is responsible for creating a real inverted image of the object, while the eyepiece lens magnifies the image further for the viewer. Understanding their roles helps us appreciate how microscope enhance our ability to see smaller details. Finally, let's calculate the total magnification of a compound microscope with given parameters: objective focal length of 2 cm, eyepiece focal length of 5 cm, tube length 18 cm, near point distance of 25 cm. Use a formula for total magnification which combines the magnification of the objective and eyepiece lenses to find the answer. So thank you. This is all about today's lecture. I hope you enjoyed the session. Thank you.